UC Irvine. And she's going to tell us about fresh off the press joint work with Dorit Aharonov on complexity of Hamiltonians in the thermodynamic limit.
Thank you, Thomas, and thank you for inviting me to speak here today. It's good to be back in Berkeley. I wanted to mention specifically that we found out very recently that Toby Cubitt and his student James Watson have been working on very similar results to these, and we coordinated our posting to the archive. So both papers were posted over the weekend and will appear sometime this evening in the US, early morning in Europe and Israel. So I encourage you to look at both papers. All right, so this is probably, I'll start out with familiar territory to many of you. Kataev sort of kicked off the study of Hamiltonian complexity by introducing the local Hamiltonian problem. It's a classical problem in condensed matter physics, but also sort of a quantum generalization of SAT. You have an input Hamiltonian, which is a sum of local terms, and two thresholds separated by 1 over polynomial in n, the number of particles in your system, and you want to accept or reject depending on whether the ground energy of your Hamiltonian is below the lower threshold or larger than the higher threshold. So, and although it's familiar territory, I want to review the definition of QMA because it's actually, there are some subtleties that will come up later in the talk. So a problem P, it's a promise problem, partitions the set of inputs into 3 categories: accept, reject, and invalid inputs. So in the case of the local Hamiltonian, an invalid input would be this case where the ground energy is between A and B, or 2 thresholds. So the problem is in QMA if there's some polynomial time quantum verifier, so that if X is in the reject category, there's a quantum witness that causes B to accept with high probability. If X is in the reject category, then no matter what witness you feed to V, it will reject with high probability. And the critical thing here for us is that if X is invalid, we have no promises whatsoever. So normally when we're proving QMA hardness results, we don't worry too much about this because we construct these Hamiltonians whose ground state reflects the answer to a computational problem. And we make sure in our construction that the Hamiltonians land on either side. So if it's a rejecting computation, it'll end up on the reject side. If it's accept, it ends up on the accept side. So we just carefully craft our Hamiltonians so that they don't generate invalid instances. In the case where we're looking at QMA as an oracle class, it's a little trickier because we're going to be embedding some computational process in the ground state of a Hamiltonian, but now we don't have any control over the queries made to the oracle. So invalid queries could be made and we have much less control over what happens. And this is sort of ultimately the reason why our results aren't tight, and I'll discuss that at the end more in more detail. Okay, so Kataev's construction was far from what is commonly studied in computational condensed matter physics for several reasons. First of all, it's non-translationally invariant. So every term is sort of tuned to the particular particles that it operates on. It's not geometrically local, it's 5 local instead of 2 local. And so sort of this kind of kicked off a sequence of results that brought the class of QMA complete problems closer and closer to the type of problems that might be studied in many body physics. So 2 local qubits on a 2D grid, 2 local on a 1D chain, and finally translationally invariant on a line. So translationally invariant means that every term is exactly the same. Now these are still finite systems. So what these results are saying is what's the complexity of determining the ground energy as a function of the system size? And that differs from what a physicist might be interested in. So typically physicists are looking at or interested in what are the properties, energy, correlation length of the ground state as n goes to infinity. So they're really mostly interested in this thermodynamic limit. And we have to, numerically, you have to look at finite system sizes out of necessity. but really we're mostly interested in sort of what happens as n gets very large. Now, this of course requires some notion of translational invariance, because if it's an infinite system, you can't specify every single term individually. So typically we think of each dimension as having its own term. So like in a 2D example here, we have two terms, the vertical interaction and the horizontal interaction. But as long as it's a constant dimensional grid, it'll be a constant number of terms. So this is what we're going to be interested in now, is what happens as n goes to infinity. And there's been some work, but there's still a lot that's unknown about the thermodynamic limit. There was a breakthrough result by Cubitt, Perez, Wolf, and later generalized to 1D systems that says that given a Hamiltonian term H, and now this is just the single term that acts on two particles, and that's part of the input, it's undecidable to determine the spectral gap as H is applied in the thermodynamic limit. Okay, and this is actually closely related to sort of phase diagrams because their H's were tuned by a weighting parameter and further developed in this later work on computability of phase diagrams. But what about energy, and what about sort of the computational complexity? We know that if all you want to know is your ground energy to a certain precision, you can just look at a finite system and determine that. So in terms of computing energies, as long as you're bounding the precision in some way, this should be a computable problem. So this was studied, but in the context of sort of an input-dependent Hamiltonian term. So as a byproduct of our main results, Daniel Gottesman and I showed that if you have, as an input, you're given the Hamiltonian term. So the entries are integer multiples of 1 over a polynomial, and you're asked, is your ground energy below some threshold or above some threshold? This is QMA X complete, and X means that you have an exponential time verifier and an exponential size witness. And the X just comes from the fact that your input now is logarithmically smaller than it would be in the size of the system. Now, it makes sense to sort of question here, does it really make sense to study this ground energy density in the thermodynamic limit as a function of the Hamiltonian term? Because usually you think of studying the Hubbard problem as a completely different problem as studying, say, the Ising model. So the H isn't so much a function of the input. H is really more of a parameter of the problem. So for different H's, I have a completely different problem. And really what you're interested in is, given a fixed Hamiltonian term, what's the complexity of computing the energy to a certain level of precision? So it's worth pointing out here that different variations of translational invariance have been studied. I'm going to illustrate this first for finite systems and then talk about infinite systems. So in the most general variety, you're given as input your size of your system, the particle dimension, and the Hamiltonian term itself. So it's specified in some number of bits. The entries are given to you. In the more stricter version of translation invariance, the Hamiltonian term is a fixed parameter of the problem and doesn't change. So the only input to the problem in this case is the size of your system. Okay, and this is the version that Daniel and I studied. And wait. There we go. And you can imagine an intermediate version of this where you have a small constant number, I put here 2, fixed Hamiltonian terms. And those are fixed parameters of the problem. And then you're given some input n, which is the size of your system. And the Hamiltonian term that you're applying to every pair of particles is a weighted average, and the weights depend on the input. This is actually the most commonly studied variety in the literature, is where you still have some input dependent aspect of your Hamiltonian term. Both are natural problems. So this is certainly a stronger version, but you can imagine a version of, say, Fermi-Hubbard, where you have some weighting factor, and that weighting factor is your parameter that's weighting two different terms. Now, what does this mean when we go to infinite systems? Now the n goes away because we don't have a system size anymore. And the first two varieties of translation invariance, where there's some input dependence, still have an infinite family of Hamiltonians to study. So if I'm interested in doing a reduction from an infinite language, I still have an infinite family of Hamiltonians to reduce to. In this last version, if I'm fixing the Hamiltonian term as part of the problem, and now I'm studying this, system in the thermodynamic limit, there's really just one number. It's the ground energy density. So you could ask, why is it hard just to compute a single number? And why should this problem be hard? So it seems like an appropriate time to give you actually the formal definition of the problem. So I'm gonna express it in 2D because that's what we study in this paper. So there are two Hamiltonian terms, and I can define the n by n grid and apply the h row in the horizontal direction to every pair of neighboring particles and h column in the vertical direction, and look at the energy density. So this is the ground energy divided by the number of particles, and let n go to infinity. So this is what we're talking about in terms of understanding in the thermodynamic limit. And what we capture here is the complexity of computing this number to a given level of precision. So here, the only input to the problem is n, which tells you the desired precision of your result. So the output, we're looking at a function problem here. The output is some number alpha, and what we require is that alpha is within 1 over 2 to the n of the true number that we're trying to understand. So fixed problem, fixed Hamiltonian, and what we're capturing here is the complexity of each additional bit of precision in the output. How complex is that to do? You could imagine a decision version of this problem in which we're asking for just the nth bit. It seemed a little artificial. And as it turns out, in order to calculate the nth bit, you actually have to calculate bits 1 through n minus 1 as well, because you could certainly verify that the nth bit of a state has energy is 0 or 1, but you have to verify that the state that you're measuring is the true ground state. So ultimately, they are roughly the same complexity. And this problem was proposed by Ignacio at a Simon's workshop a few years ago. So that's where we got the idea to work on this. Okay, so our results are that this problem is contained in function exponential time to the QMAX and hard for function exponential time to the next. So there's a gap here of classical versus quantum, and I will speak to that at the end. Many aspects of our construction can be made quantum, but there's a sort of an obstacle in terms of the invalid queries that I'll discuss at the end. We still need a quantum construction because we're still using the circuit to Hamiltonian construction of Kitaev that represents a ground energy. So we start with some generic function that's sitting inside fx to the next. And so we have to encode this entire function, which is an infinite object on an infinite number of inputs, into a single number. But the number itself is infinite precision. So what we do is we encode the value of the function f on different inputs in different parts of the binary representation of this alpha naught. So each additional bit gives you information about a new input to the function f. Okay, and we use, to start, we use a construction that was initially used by Cubitt, Garcia, Perez, and Wolf, and of Robinson tiling. And this is a fixed set of tiling rules that in its ground state produces an aperiodic structure of squares of increasing size, of exponentially increasing size. So for every k, there are squares of size 4 to the k, and the density of those squares in the infinite plane is 1 over 4 to the k squared, roughly. And so this serves as a layer of the Hamiltonian and sort of breaks the symmetry of the infinite plane. And what we do is then on the second layer, we embed a construction of a 1D translationally invariant Hamiltonian for finite chains. So sort of the tiling rules enforce that on this top row of these squares, what's happening on the layer 2 is some finite construction, some other Hamiltonian term that we're applying. The net result of this construction is that ground energy density in the thermodynamic limit is this infinite sum. It's the ground energy for 1D chain of length 4 to the k divided by the energy density of the squares. So we're layering on top a construction for a finite system. Okay, so basically what we've done now is reduce sort of the infinite problem to the finite problem. And so the goal here is now to come up with a construction for finite chains that answers a computational problem. And so let's just take a closer look at this infinite sum. So if I were to represent this sort of graphically, this is what the ground energy looks like. The red is all zeros, and that's sort of the right shift that's achieved by this 2 to the 4k. So each of these terms is sort of staggered. And then what we're summing up is the ground energy for a 1D chain of a particular length, 4, 4 squared, 4 cubed, etc. Now, notice as we have it here, these terms are staggered by only 4 bits, which doesn't give us quite enough room to express a function. So the first step is we only use squares of a certain size. We only use squares where the exponent is a perfect square. So 4 to the x squared, 4 to the x plus 1 squared, etc. And so what this allows us now is it gives us a little bit more real estate in this binary representation of alpha naught to express the value of the function. So a couple things here. So it's these bits here highlighted in yellow that's going to give us the answer to sort of the function that we're encoding in this ground energy. Now, one thing to notice is that in order to uncover these bits, I have to be able to subtract off all of the previous terms. So these alpha naughts in general are going to be the lowest eigenvalue of a finite matrix. Typically, it's going to be the Laplacian of a path graph or a cycle graph plus some constant. Okay, so they're not going to be nice, clean, rational numbers that will fit neatly into a finite space of the binary representation. They're going to be infinite quantities. Moreover, we have to be able to subtract off all of the preceding terms in order to uncover the bits that give us the value of f for a particular x. So that means we have to have very precise bounds on these lowest eigenvalues. Typical results on Hamiltonian complexity really only have to be lower bound or upper bound these values. So you have to show that the ground energy for accepting computations is lower than some value, the ground energy for rejecting is higher than some value. It doesn't have to be too exact. In this case, we require very precise analytical bounds for the ground energies in order to be able to calculate these numbers and uncover the bits that we need. And in this case, the expression that we get is we come up with a construction where we can get exact bounds, analytical bounds, and the lowest eigenvalue is of the form 1 minus cosine pi over L. So, and L is some integer. It's bounded by a polynomial in the system size. So if I can estimate this value to within a given precision, I can uncover the integer L, and then I can express this value to arbitrary precision using sort of a Taylor expansion. So, one of the techniques that we had to develop were exact bounds, constructions where we could get precise exact bounds on the lowest eigenvalue. Okay, so as I mentioned, so we've reduced our infinite problem to a finite problem. So the finite problem is also, I think, of independent interest. We have a problem parameter, which is the Hamiltonian term and some constant. The input is some number, and we want to compute the ground energy of our system on a finite chain of length L to with some precision. So this is sort of the function version of the problem. Daniel Gaddis and I studied the classical sort of decision version of the problem and showed that it was QMA complete. And our results are that this function problem is contained in FP to the QMAX and hard for FP to the next. And again, there's this sort of quantum classical gap in our results. Okay, so just a little bit of a word. We have sort of an exponential difference between the finite and the infinite case. In the infinite case, we're given n, which is the desired number of bits in precision. So we want to get within 1/2 to the n. In the finite case, the input is n, the size of the system itself, which is, and we want to get within 1/poly poly of that. So roughly in the infinite case, approximating alpha naught to within 1/n requires a system size of polynomial in n. So this essentially requires a system size of 2 to the n. Since the input is expressed in binary n, that results in a double exponential. From an expressibility standpoint, when we're doing a reduction, we can use every single value of n to encode the answer to a problem. In the infinite case, the best we could hope for is recording the answer in every single bit of alpha naught, which requires the system size to double for every solution that we want to encode. So that accounts for the double exponent. And so this is closely related to a line of work initiated by Andres in 2014, which is about approximating the value of local observables applied to low energy states of a given local Hamiltonian. So this is arguably closer to sort of capturing sort of the challenge of a computational condensed matter physicist. I mean, they're not given these arbitrary bounds from a local Hamiltonian. They just have a Hamiltonian, they want to know something about the ground state, or they want to know the ground energy. And this type of problem naturally leads to oracle complexity classes. Because at the end of the day, you not only have to, say, measure the value of the local observable on some state, you have to verify that it's the ground state itself. And all of the upper bounds are some sort of binary search to a QMA or a QMAX oracle in which you're sort of verifying that the energy of the ground energy of your system is a given value. So oracle complexity classes seem to be inherent in this type of problem. So all of the results in this sort of line of work make use of sort of an old technique, which was used to show, study the optimization version of certain NP hard problems and show that they're hard for the class FP to the next. And the idea is you're taking some function, and I'll describe it here in terms of our complexity classes in FP to the next. So F is computed by a polynomial time Turing machine that makes a polynomial number of queries. It has access to an oracle in next. And so it has access to an oracle for some language that has an exponential time verifier. And we want to embed this problem into a Hamiltonian so that if there's a good approximation of the ground energy, we can then capture the value of f of x. okay? So we have to sort of make sure that we're embedding the correct computation in the ground energy. Now, so the scheme basically is a cost function, and I'm looking here, Y is a string that represents my guesses for what the oracle responses are. Okay, so I have to simulate this P to the FP to the next oracle. And for a particular string of guesses, then it's just a polynomial time computation on input X and the string of guesses Y. So we're going to devise a cost function that ensures that the minimum value of this cost function happens for the correct string. Okay, so once I have X and I have my guess for the oracle responses, then I can certainly generate all of the inputs. I can simulate P, I have my guesses for the responses, I can go through and generate all of the inputs that I would generate to the oracle. Okay, so just a rough sketch of how this cost scheme works. I can use my verifier to verify yes guesses. I can't verify no guesses. So I can verify yes guesses by simulating the verifier. And if it's a rejecting computation, I'm going to have a large catastrophic. Okay. If it's for every no guess, I can't simulate that, but I'm going to have a much more modest cost. Okay. So I'm sort of penalizing no guesses just inherently, and I'm penalizing incorrect yes guesses catastrophically. So the costs have to be adaptive in this case because the queries are adaptive. So the costs have to decrease exponentially because if I have an incorrect guess on one particular, the benefit I might get for using an incorrect guess on one query has to outweigh any benefit I would get for all of the rest of the queries. So necessarily in the scheme is an exponentially decreasing cost function to make this work. So the costs have to depend on the input. So the challenge for us here is to implement this in a translationally invariant way. So I have to implement this cost function, but I have to use it using a finite Hamiltonian. So we use Kataev's classic circuit to Hamiltonian construction. So this results in a ground state where we have some clock and some computation, and the ground state is the uniform superposition of all points in this computation. Typically, this is 1/2. This results in a matrix that's 1/2 times the Laplacian of a path graph, and a +1 depending on whether the computation is rejecting or accepting. So this is what gives us the gap. I'm going to skip over this part for the interest of time. Our construction uses a cyclical clock, so it's a cycle. So the propagation Hamiltonian is the Laplacian of a cycle. Every computation, accepting, rejecting, there's no accepting and rejecting, every computation has 2 consecutive 1/2 penalty terms. And we give exact bounds or an exact expression for the ground energy or the lowest eigenvalue of this matrix, which is 1 minus cosine pi over L plus 1. So this is precise. And what this allows us to do is it allows us to calibrate the energy of the ground energy by varying the length of the cycle. So I can have shorter cycles, which are going to have higher energy, and bigger cycles, which are going to have lower energy. And this is how we implement that input-dependent cost function. So the computational process basically runs the binary counter and some checking. I've only got a couple more minutes, so I will. So basically what happens is we run a process forward and we run a process backwards, and that allows us to end up back up in the same state, and we just repeat this some t number of times. So there's an iteration through this loop that's completed t times, where t is some variable, and this is what allows us to regulate the length of the cycle. Running the process forward and then running the process backwards guarantees that we end up back in the same state, and that the computation will also have this cyclical structure to it. So there are certain penalties that check for that the computation is doing the right thing, which is that the penalty term for an incorrect start and penalty terms to make sure that the timer length has the correct length. So this process checks various things. So it checks that the input is correct, so that we start on the correct input. It checks whether the verifier is rejecting or not. It checks whether the timer, which is regulating the length of the cycle, is correct or not. And basically we're computing the length of the timer, which is implementing this cost function. So this cost function, which is which is going to reward the correct set of oracle gases, is going to ensure that the correct string results in the largest T, which then results in the smallest eigenvalue for the matrix. So this function encapsulates the cost function. It also encodes the output to our the function that we're reducing from, so that we can reduce and recover the input. And so another feature of the analysis is that we have to be able to sort of penalize computations that don't have, so for example, that have rejecting computations or the incorrect timer length or start on the wrong input. And we can do that. These have a periodic cost. So these happen, if I look back at the computation, these happen once a cycle, then it gets penalized. So the resulting matrix that I get is, again, the Laplacian of the cycle, but now the penalties are happening once every cycle through this graph. And so we also need a lower bound for this, which is 1 over a constant times the interval between the penalties. And so that also required an additional analysis to get something that was independent of the size of the matrix. Okay, so this is the essential outcome, is that this Hilbert space is divided into blocks. If Y has the incorrect yes guess, then there's a catastrophic cost, which takes it out of the running. Otherwise, the ground energy of the block is this function, and we ensure the fact that that it's going to be minimized or maximized for the correct Y. So for a given approximation of lambda, I can get this correct value of this function, from which I can then extract the output to my function. Okay, so let me just say a couple of words now about sort of the biggest open question is sort of to tighten up the difference between the hardness result and the containment result. I mentioned at the beginning that there are several differences between NP and QMA. QMA has a quantum verifier, QMA has a quantum witness, and it has invalid queries. So you can imagine an intermediary class, which is a language version of QMA. So quantum witness, quantum verifier, no invalid instances. As it turns out, our construction can easily be made hard for this oracle class. So since this isn't a class of particular interest, we simplified our lives and wrote it up for the classical version. But we can handle quantum witnesses and quantum verifiers. It's just the invalid instances that throw everything off. And just to sort of illustrate why that's true, so this circuit to Hamiltonian construction simulates a verifier for oracle languages on queries. At the end of the day, the acceptance probability is translated into the energy. And if you have invalid queries, it results in a completely unknown and uncontrolled minimum energy. So if you're trying to embed the answer of a computational problem into this energy, it's problematic if you don't know what it is and you can't control it. So that's really where the problem comes from. And interestingly, this is an issue even in the non-translationally finite case. So we leave as an open question, what's the complexity of the function version of local Hamiltonian? So I give you a Hamiltonian, not translationally invariant, and I ask you to compute the ground energy of this Hamiltonian to within a given level of precision. And so we don't know the complexity of this question. So it seems like a natural question. And so it's certainly a challenge in the infinite translationally invariant case, but it's also an issue for the regular garden variety local Hamiltonian problem. So, and I will end with that open question.
Thank you. On behalf of everyone, thanks a lot for the talk. So we have time for questions.
Daniel raised his hand.
Yeah, hi Sandy. So do you have a bound on if it's just a purely classical Hamiltonian? Do you know what happens then?
We don't know. Right, so it turns out what the computations that we're embedding are all classical computations because our verifiers are classical, but I don't know the complexity. It might be that, there's, I got a peek at the paper by James and Toby, and they might address that problem. So I'm not sure though, if it's purely classical. And for us, the problem was this issue of embedding into the Robinson tiling. So we kind of needed the quantum version because the ground energies are small in the quantum version. So when you look at the circuit to Hamiltonian constructions, those result in 1/poly ground energies. And it's a question of the robustness of the Robinson tiling. So you have to make sure that the costs of this 1D chain aren't so large that they outweigh the costs of violating the Robinson tiling. So you have to make sure that the optimal ground energy is going to be a correct Robinson tiling and that it's going to be worth it to incur the cost of these additional finite chains because a Robinson tiling error would be so large in comparison to it. So that's sort of where we sort of ran into the problem.
So
So
then James in the chat confirmed that the paper does contain the classical version. Sev raised his hand.
Hi, Sandy, can you hear me?
Yep.
Great, wonderful talk. I just had a quick question about this paper of Krentel, right, that you guys mentioned. Right, so there's it's a paper I've thought about before, and but one thing I've always wondered about that is that, I mean, in that paper, they show that if you have a polynomial number of queries to an NP oracle, then that allows you to compute kind of exponential bits of precision to your optimization problem, right? And the problem when you think about quantum analogs of this is that the oracle only gives you 1/poly precision, right? So it's not clear that doing a polynomial number of queries to this thing can give you exponential precision in anything, right?
Right.
And I think you guys seem to get around that because you're querying a QMA exp oracle, let's say, or an exp oracle. So you really do get that very fine precision. So I was totally at a loss as to what to do with like Krentel's result, right? If you think about p to the QMA, let's say, versus p to the QMA log. And
Right.
I'm just wondering if you guys have thought about that or?
Yeah, we didn't, because of the translational invariance, we're sort of inherently in this domain.
Yeah, that comes naturally. That's right. Yeah.
We're in QMAX, so we didn't have that. We didn't have that issue. So we didn't think of it. And another thing that's sort of related to that is your result that, a polynomial number of adaptive queries is the same as an exponential number of parallel queries. And we tried to think of ways in which that would help us reduce the dependence on the input. But in our construction, that didn't seem to work. So we stuck with the adaptive version. So.
Okay, good. Thank you.
So can I ask a question?
Sure.
Yeah. So in one of the slides, you mentioned that by blocking, you can estimate the ground energy density up to error epsilon.
Mm-hmm.
Is that the best algorithm you would imagine for this problem, like just from computational point of view?
You mean the binary search? Just
right, like to compute the ground energy density up to error epsilon, you could make blocks of size poly 1 over epsilon and then just solve locally.
Yeah, and that's basically what we suggest doing. Is that's the best known. So you just basically solve it. You have a finite system, and then you have queries to an oracle that will tell you, that will help you compute the ground energy of that finite system, and then the sort of the error around the edges is small compared to the bulk of the system. So that's the best. That's the best we're aware of.
I see. And is that what that gives the containment in FP to the power QMAX?
Yes.
Okay. Thanks.
So it's looking at finite systems. Exactly.
Okay.
I wanted to ask about, so you presented the containment for starting from a FP to the NX algorithm. And then you kind of said, well, it sort of seemed like straightforward that you can extend it to the, I guess, FP to the QMAX, assuming you don't have to deal with this promise. So is that the case? It is straightforward. When you presented it, I thought this is never going to extend because you list the.
Okay, so it's for the infinite case, we'll need QMA1. And the reason is, the best you can do is, and the reason is kind of I described earlier, is that you need to be able to determine these ground energy densities exactly for accepting computations. And the ground energy always depends on your likelihood of acceptance or your probability of error. So we can't afford any error in the accepting computations. So QMA1 is the best we can hope for the infinite case. Most everything in the construction generalizes. There is a little bit of extra work to be done because this Hamiltonian term that penalizes a rejecting computation is now not perfectly diagonal on your standard basis anymore. So there's a little bit of extra work to do, but it's not too bad. So it can be done. Yeah.
But the class, and so this is just ignorance, but the class, however that would be, so that doesn't contain anything that's not in NP or what, like a QMA.
XL, you mean the language version of QMA, is that?
Yeah.
Yeah, we don't know if any, this is sort of the first that class occurred to us, only because that's what comes out of the construction. So I'm not aware of any interesting problems in that class or complete for that class.
Yeah.
If we had, we would have written up our results for that hardness, I guess. So.
Okay, thanks. We have a minute or two for some more questions.
If I may bug you again, since there's some time, you mentioned this nice open problem at the end, right, with the function local Hamiltonian?
Yeah.
Yeah, so if I remember correctly, Andres's paper in 2014, right, had this claim for something similar, not exactly the same, right? It's still a decision problem that wants to know if the exact energy is, it's upper and lower bounds on the energy. Yeah. And I think there he defines a class like dQMA or something like this. That's right. That's a quantum analog of dP.
You're given the value and you want to verify that value.
I think so, yeah. But it's not the function version. You're not outputting this thing.
Right.
Right. So, I mean, have you guys thought about that connection, or, I mean, that's the obvious place to start, I guess, right?
Yeah, that is, and that, so that there's an analog question in NP too. So, is your min value this, exactly this value? Exactly. And I think, I don't know how that works to the fact that Andres did sort of originally overlook this invalid query issue.
Oh, yeah,
so,
yeah.
So that was, I think, part of it. An understandable mistake, because we did for a long time as well. So. So I think that might be the issue there. So, but that is a good place to start, is if you're given the value and just sort of to verify a particular value is within epsilon of the ground energy. Certainly be a good place to start.
Okay, great. Thanks. Let's thank Sandy again for the talk. Thanks a lot. So the next speaker of the morning is